to develop rules to to determine the derivative of a product of functions or a quotient of functions. So let's look at the product rule for h of x equals g of x, and I keep forgetting my favorite little pointer. Product rule for h of x equals f of x times g of x. Okay, we have two products of functions. We want to determine their derivatives, aka what would be h prime of x. Okay, so what we're going to do is interpret this visually. We can interpret f of x times g of x as a rectangle of area f times g. So this area in blue right here is just h. Now if we extend g by a little bit, what we'll call delta g or dg, and extend f by a little bit, what we call delta f or df, we're going to get a change in area. This change in area is represented by the kind of vanilla looking section right here. Vanilla, nice little rhyme there. And we'll call this area dh, or delta h. So dh is going to be equal to dfg, which is going to be a change in area. So if we apply geometry here, we see that dfg is going to be equal to the area of this vanilla section plus area of this vanilla section plus area of this vanilla section. The area of this vanilla section is going to be f times delta g, or dg. The area of this section is going to be df times dg, and then the area of this section is going to be delta f times g right here. So as a result, we have that our dh, our change in area, is f dg plus df dg plus g df. So now what we're going to do is we're going to cross out the df and dg. We're just going to say equals 0. Again, the idea here is that these df's and dg's, dy's, dx's, whatever you would call them, are infinitesimally small. They're oh so very, very small. They're so small that if we multiply two of them together, we're going to get 0. The same way that if you take like 1 over 1,000 and multiply it by 1 over 1,000, you're going to get a number that's so small that's essentially equal to 0. So now what we end up with is dh equals f dg plus g times df. So now if we divide both sides by dx, we're going to get dh divided by dx equals f times dg over dx plus g times df over dx. And this yields for us the product rule for derivatives. If we have h equals f of x times g of x, then the derivative of h is equal to f times the derivative of g plus g times the derivative of f. A nice, useful result that you can get from geometry. There is a proof, but the proof is very scary to look at, and I just don't want to do it. Not good. So example 1, the product rule for derivatives. What is the slope of the tangent line at x equals 2 of g of x equals 2x cubed minus 7 times x squared plus 3x? So here, my computer seems to have frozen. I don't know what's happened. There we go. So here we take the derivative of, we have 2x cubed minus 7 times x squared plus 3x. We take the derivative of 2x cubed minus 7 times x cubed plus 3x, and then we add on to that 2x cubed minus 7 times the derivative of x squared plus 3x, okay? So as a result, we're going to get 6x squared right here times x squared plus 3x, 6x squared being the derivative of 2x cubed minus 7, and then we're going to have 2x cubed minus 7 times 2x plus 3, which is the derivative of x squared plus 3x. So now simplifying, we're going to get 6x to the fourth plus 18x to the third when we simplify right here. And then expanding this term right here, we're going to get 4x to the fourth plus 6x cubed minus 14x minus 21. So as a result, simplifying our terms, we're going to get 10x to the fourth plus 24x cubed minus 14x minus 21. And then if we want to evaluate this at x equals 2, we just plug in x equals 2. And we get a resulting answer of 303, which is a big number. Hopefully, realistically, you won't see a number that big on the exam. But the idea and concept is still the same. Note that if we had expanded this out originally, we could have evaluated this just using the rules from 2.1, power rule, specifically the power rule, and you would get the exact same answer here. Quite cool. So now we look at developing the quotient rule for derivatives. Specifically, if we have h of x equals f of x divided by g of x, what is the derivative h prime? So what we're going to do here is we're going to manipulate this by first multiplying both sides by g. H of x times g of x equals f of x. So now we can apply the product rule. H prime times g plus h times g prime equals f prime. So now we have h prime, we just got to solve for it. So we're going to subtract h of x times g prime of x from both sides, and then divide both sides by g of x. So now what we're going to do here is we're going to substitute in h of x equals f of x divided by g of x to get f prime of x divided by g of x minus f of x over g of x, again where we substitute in h of x, times g prime of x divided by g of x. So now what we're going to do here is we're going to combine the expressions on the right-hand side by using a common denominator. So what that means is we're going to multiply the f prime divided by g of x over g of x. So that way we have a common denominator of g of x times g of x. So now we're going to get, we can combine the two expressions to get f prime of x times g of x minus f of x divided by g prime of x divided by g of x squared is equal to the derivative of h prime of x. So we've now developed a rule for a derivative of h where h equals f of x divided by g of x. The derivative is going to be the derivative of your numerator times your denominator minus your numerator times the derivative of your denominator divided by your denominator squared. Or in terms of f and g, the derivative of f times g minus f times the derivative of g divided by g of x squared. Note here that you're going to have a vertical tangent line whenever g of x is equal to 0, because you have this g of x squared in your denominator. So you're always going to get a vertical tangent line when g of x equals 0. So example 2, quotient rule for derivatives, okay? I did not copy and paste this into here, oops. So this is f and this is g, so our function is 2x cubed minus 6 divided by x, okay? So we want to find the derivative of this function here. So 2x cubed minus 6 is our numerator and x is our denominator. So we start off the derivative of our numerator times our denominator minus the numerator times the derivative of the denominator divided by the denominator x squared. So as a result, the derivative of 2x cubed minus 6 is 6x squared. The derivative of x is just 1, so we're just going to end up with 2x cubed minus 6 on this right-hand side right here. So as a result of simplifying right here, simplifying this term, we're going to get 6x cubed minus 2x cubed plus 6 divided by x squared. We can factor out the squares, so the 6x cubed we can divide out the x squared on the bottom. So the 6x cubed minus 2x cubed becomes 4x cubed, which when we divide by x squared becomes 4x. And then the 6 is just going to become 6x squared. So our derivative, if we evaluate it at x equals -1, is just going to be evaluated by plugging in x equals -1 in, which gives us a derivative of 2. Notice how h prime of x has a vertical tangent line at x equals 0. We can see that because we have this x squared in denominator right here, which is going to blow up when x equals 0. Thus confirming that h is not differentiable when its denominator is equal to 0. And these are the rules for evaluating derivatives of products and quotients.